So we're talking about the Rankine cycle now. The Rankine power cycle. We're doing it mostly as an idealized thing where we're assuming no internal irreversibilities. And we're going to use that. Yes?
Are the Rankine solutions going to be coming up soon?
Oh, there's no solutions?
Yeah, there are.
Are they going to be coming up soon? Maybe let's go through those in class as we go.
Yeah, absolutely.
Yeah, let's do that. But so we have this idealized thing that's going to let us calculate some stuff for idealized things in general, which is cool because we've talked about like efficiency of an ideal power cycle, but I just had to give you the stuff. Now we can calculate those things. And it, besides being an ideal power cycle that lets you calculate stuff for ideal power cycles in general, it's a model of a specific type of cycle that's actually used in power generation. So we can also talk about it as sort of an applied, useful thing. And remember that it, on a temperature entropy diagram, it looks like this. State 1 is there. That is on the side of the vapor dome that represents a saturated vapor. It goes down to here. This is state 2. The process from state 1 to state 2 is an isentropic turbine. What does it take for something to be an isentropic process?
No change in entropy.
Yes, but yeah. So that's that's like what that word means, right? And what does it require for an isentropic process?
No heat, no.
Right, no heat transfer and no irreversibilities, internally reversible. We did a calculation. We have equations for calculating entropy change for an ideal gas if you have an isentropic process. And we talked about calculating the temperature change in an isentropic process. Okay.
That's when you do like the P sub R or whatever.
Yeah, that's right. Yep, exactly. And then it goes from 2 to 3. So this is state 3. This is the constant pressure, or other word for it is isobaric condenser. So that's the process that takes it from a mix of, so at state 2, it's a mix of liquid and vapor, and it goes to a saturated liquid. And then it goes up to state 4 here. And that process is an isentropic. Which process is this? Pump, yep. And notice one thing about the pump process. If you got to choose, so someone says, you got to calculate all this stuff by hand. Change in entropy, change in internal energy, change in, I don't know, all sorts of stuff. What state would you want that process to take place in? What are the most simplifications for? Incompressible.
Oh,
Yeah.
You can do everything with incompressible stuff, you know? And so notice that this is going from a saturated liquid to a compressed liquid. It's liquid the whole time. We can treat it as incompressible. And so this pump state is, you would think that's going to be where we know the most stuff, and it is going to turn out that way. Okay, so remember that this is a liquid the whole time. And then from 4, it heats up until it's a saturated liquid, and then it changes phase to a saturated vapor, and this is the boiler.
question.
Yes.
From 1 to 2,
Mhm.
turbine, wouldn't that have like like X bar, you'd have some liquid, some gas in between one another?
Yeah, once you leave state 1, yep, it's the quality is changing that whole time. Yeah, that's right. Yep.
Okay. And then, because you were saying that you didn't want, if you were to design it,
Mhm.
any liquid at all inside the turbine.
Right. Yes, that would be better for for maintenance on the turbine blades.
Yeah.
Um,
I think you were showing some other ones with the
Right.
outside.
That's right. Yep.
Yes.
And we're going to do a bunch of calculations about efficiency. Last time we showed, so that's what we're doing right now, is going through a bunch of derivations about calculating the efficiency of this power cycle. So that was last time. And today, we're just deriving these things for these ways of calculating the efficiency of this cycle. The first one we got, which I think is interesting, is we talked about just in passing a couple weeks ago that the efficiency, you can calculate that based on the temperatures at the high and low temperature reservoirs. And we showed now that for this, for the Rankine power cycle, the efficiency is equal to 1 minus the temperature at the condenser minus the temperature at the boiler. Okay? Well, I'm trying to be consistent with these. Let's call that TH. Okay, so we figured this out last time. And now we're going through the process of, so we're in the process of calculating the efficiency in terms of enthalpies at the different states.
Does it matter that last time we said we did things in terms of average temperature?
Yeah, right.
Different for us, or is that just because we don't do the same stuff?
So when I introduced it, so last time we figured out more, sort of more precisely that it's this. Before that, we were just sort of glossing over the fact that we're just going to call that the temperature at the condenser and the boiler, those average temperatures. But yeah, now we know that that's an average temperature, yeah.
Do we actually
Of the working fluid.
Okay.
Okay, so we did 2 of the processes. So first we went from state 1 to 2, and that was the isentropic turbine. Also, I want to point out that, so I'm going through these derivations to come up with results, and those final results are important to keep in mind. But you also want to follow these steps, because in problems, you're going to have to do kind of versions of steps like this, okay? So you're trying to get 2 things out of this. You're trying to follow how these calculations are done generally, and you're also trying to, somewhere you want to have these take-home messages written down or in your head. Okay, so we figured out that for the turbine, the work that you get out of the turbine divided by the mass flow rate is equal to the specific enthalpy at state 1 minus the specific enthalpy at state 2. And then you go to the process that takes us from state 2 to state 3. That's the constant pressure isobaric condenser. And for that, we get that. Hi. Sure. The rate of heat flow out at the condenser divided by the mass flow rate is equal to H2 minus H3. And remember that in these derivations, one important step was recognizing that like thinking about, so we started with the control volume form of the first law, right? We did it all with the control volume first law. And in one of the important steps, we had to think about, okay, now when we talk about the condenser, we're talking about QC leaving the system. How does that relate to the sign convention of the first law? And so we had to switch the signs of the heat, okay? And so we're gonna have to do that at each step. At the turbine, we thought like, okay, well, the turbine, what we're calling WT, is work leaving the system, okay? Well, that's the same as the sign convention for the first law. So here, we didn't have to change the sign. Okay, so remember that's something to think about at each one of these steps. Anybody have any questions about that? So I'm going to try to bring that up in each step. But now we're going on to the first step that we didn't do last time. So now we're going to the process that takes us from state 3 to state 4. That is the isentropic pump. We're going to assume this is steady state. And we're going to assume that the change in potential energy, the change in kinetic energy, and it's isentropic, so we know that Q dot also, they all have to be equal to 0. We're going to assume that. And so we start with the control volume first law. Cancel heat, kinetic and potential energy terms, and dEdt. And we get that W dot is equal to M dot times the quantity HI minus HE. All right, well, for an isentropic pump, for a pump, is work leaving the system, being output by the system, or is work coming into the system? Coming in. So I'm going to change this to W dot sub P. And I guess I'll divide it by M dot here. And so W dot sub P over M dot is HE minus HI. I switched the signs on stuff. And so the final form is W sub P dot over M dot is equal to, our exit is 4, and our inlet is 3. Okay. Well, that's not all for the pump. We know a little more because since the working fluid is incompressible through this whole process, we know that V3 is equal to V4. And so the TDS equation, the second TDS equation says T ds is equal to du, nope, dH minus VdP. This is an isentropic process, so this term goes away. And so we have dH is equal to VdP. And we can integrate both sides. But notice that this V is constant. Because it's incompressible. And so the change in H is equal to V times the change in P. So H4 minus H3 which, notice, is equal to our WP dot over M dot. Is equal to the specific volume at either one of those two states times the pressure at state 4 minus the pressure at state 3. So in half the problems we're going to do for this cycle, instead of being able to figure out the enthalpies, you'll be able to figure out, or you'll be given stuff about the pressure, and and we'll do that instead. So notice on this one, look to take advantage of the incompressibility. For the pump process.
Are there gonna be problems where you have to start it somewhere and find the numbers for the whole system, and it's just best to start at the top of that?
Well, what we're heading towards is the efficiency of the system. And so we're heading for a whole, an expression for the total efficiency of the whole cycle in terms of enthalpies. But sometimes you won't be able to get the enthalpies for the pressure with what's given, but you can come up with it this other way. Okay, so basically everything is going to be about calculating efficiencies. Okay, and then the last one is going from state 4 to state 1. This is an isobaric process through the boiler. We're going to assume this is steady state. We're going to assume that potential energy and kinetic energy don't change. And also this is rigid, so there's no work. So the change in potential energy, the change in kinetic energy, and W dot, we're going to assume those are all 0. And so start with the control volume first law. Cancel the kinetic, potential, cancel the work, and dE dt. And we get that Q dot is equal to M dot times the quantity. If you're moving the H stuff over to the other side of the equation, this will be HE minus HI. And now you have to think about the direction of the heat. In this case, at the boiler, heat is coming into your working fluid, into your system. That agrees with the first law sign convention. So we don't have to change the sign this time. So we get Q dot boiler is equal to, let me divide out so Q dot at the boiler divided by M dot is equal to HE minus HI. And so Q dot over M dot is equal to the state at the exit, that's H1, the state at the inlet, that's state 4. And so there you go for your boiler. So notice at each step, we had to think about whether Q dot or W dot agreed with the first law sign convention. So we got that, let's see, at the turbine, W dot at the turbine was equal to the W dot from our equation. At the condenser, Q dot was negative Q dot from the first law. You understand what I'm talking about here? The work for the pump was negative work dot from the first law. And then Q dot for the boiler was equal to Q dot from the first law. You know, these are the ones for the device. These were the ones from the first law for control volumes. Okay, so we've come up with expressions for kind of like the input or output at each one of those processes in terms of enthalpies. Now we want to use those to calculate the efficiency. And one thing about our expression for the efficiency here, we're going to see it's a little different. Where we start is going to be a little different than how we did it when we were talking about the Stefan Boltzmann or the Boltzmann
They should have
statement.
After scientists.
Yeah, I know, exactly. But you know, the first time when we talked about that abbreviated form of the efficiency, we just said like, okay, for a power cycle, you want to take the work and divide it by what you put in at the boiler, right? Well, now we have another work. I mean, now that we're thinking in detail about like a specific process, it's not just a matter of how much work we get out at the turbine, because then we have to put some work into the pump, okay? So we're going to define the efficiency as the work we get out at the turbine minus the work we have to put into the pump. Okay, we didn't have that before. Divided by the heat we have to add at the boiler. And this, we can rewrite this as W dot at the turbine divided by M dot minus W dot at the pump divided by M dot divided by Q dot at the boiler divided by M dot. And now we have all these, you know, all these box things are things we can just put in place of these. So our efficiency is equal to W dot over M dot at the turbine. Well, I have it here in my notes. So this is H1 minus H2. And then subtract from that W P dot over M dot, which is H4 minus H3. Divided by Q dot at the boiler divided by M dot. So that's H1 minus H4. And now you can rearrange this a little bit. So I'm going to write this as H1 minus H4 minus H2 minus H3 all over H1 minus H4. And it's starting to take this form that we're sort of familiar with. So you can write this as 1 minus the quantity H2 minus H3 over the quantity H1 minus H4. And this form is nice because this is always positive, and this is always positive. Well, notice one thing here. From the definitions of QC dot over M dot and QH dot over M dot. This equation above, you can rewrite that as 1 minus QC dot over M dot divided by QH dot over M dot, which is the same thing as 1 over QC dot over QH dot, which is the same as 1 minus QC over QH. So even though we started with a little bit different, a different starting point for our definition of the efficiency, because we had to take into account the work that you're putting into the pump, we come up with the same definition in terms of heats that we had before. Okay. And what can we see from this? So regarding the efficiency of the entire cycle, we saw last time, we had seen it before, but we did the math on it last time to see that we could write the efficiency as 1 minus the temperature at the condenser divided by the temperature at the boiler. Okay, so from this you can see that it gets more efficient as TC goes down or TH goes up. Okay, so we saw that last time. This time we can also see using our sort of final equation here, H2 is the enthalpy going into the condenser, and H3 is the enthalpy coming out of the condenser. Okay, so we want the pressure in the condenser to be as low as possible. And this is the enthalpy going into the turbine, no, going into the boiler. 4 is going into the boiler. 1 is coming out of the boiler. And so obviously we want the denominator here to be as big as possible. So now we see that from the equation that says efficiency is 1 minus the quantity H4 minus H3. No. What was that?
The H2 minus.
Yeah, H2 minus H3 divided by H1 minus H4, that this cycle gets more efficient as the pressure in the condenser goes down or the pressure in the boiler goes up. Those are the two isobaric processes. Okay, so you want, in the boiler, you'd like to have super high pressure and super high temperature. And in the condenser, you'd like to have super low pressure and super low temperature. Okay, so that's what you would like mathematically in order to make the efficiency better. There's one more calculation that
But the only
Yeah.
issue with that is, like you were saying earlier, lower the pressure, the lower the temperature, the more it's going to condense.
well, yeah, actually pressure, if you could make the pressure super low in the condenser, then things would stay a vapor at a really low temperature.
Yeah.
But yeah, I mean, but you're right overall that that's something that has to be considered. So we'll talk about that later on when we get into practical considerations. But there's one more thing, one more term, you know, one more definition. That is the back work rate, it's called. And you want this to be low. And the back work rate is defined as the work that you're putting into the pump divided by the work that you're getting from the turbine. It makes sense you want that to be low, right? Like it doesn't help you to have a really great working turbine if all of the energy you're getting from the turbine is going into pumping the fluid from a low pressure to a high pressure. And so this is equal to this, you know, this little trick we're going to do all the time. And now you can go back to the definitions of W dot sub P over M dot and W dot sub T over M dot. And this is equal to the enthalpy at state 4 minus H3 divided by H1 minus H2. Any questions about that? Okay, so, you know, I think we still are not, we're almost at the point where we can work on problems. You maybe could fight your way through problems, but I'll do an example at the start of next time, and then you'll be able to do some similar problems to that. But as you work on problems, remember that a lot of the clues of how to do this stuff, they don't come from the boxed equations. They come from the approach, from going from the control volume first law to those expressions, you know. So if you get to a point where you don't know what to do, the hints are likely to be in the steps of those derivations. Okay, any questions? All right, let's stop there, and next time I'll get into an example problem.